Hi, in the last session, we designed a serializer in VHDL, which was configurable and capable of converting parallel data into a serial data stream. Now, let's talk about memory modules in VHDL. For example, random access memory or RAM or read only memory or ROM. In this session, we will be designing a single port module and a dual port module for a RAM. These memory modules are widely used in most of the FPGA designs for storing data. So they are quite important to learn. So let's start. Now, before we design them, let's understand few important things in FPGA designing about these memory modules. So in FPGA, data can be stored by two ways. Let's discuss the first approach. FPGA contains many number of registers and synthesis tool analyze your VHDL code and detect some group of registers to form a RAM module. These registers are then grouped together to form some kind of a small memory. We generally call them register banks. These register banks are good for small memories because your synthesizer can infer these banks from your VHDL code. This means you do not need to write specific code to implement these RAM modules. So by default, FPGA can use these register banks to implement your memory in your projects. However, there are some disadvantage of register banks, especially when you are needing a larger memory elements for your designs. And if you only rely on the register banks, then they can quickly exhaust in the FPGA flip-flops. And it is not good because it will limit your ability to implement bigger systems that need lot of resources and elements from your FPGA. So we are needing some different way in such cases for more data storage. And as a second way, we can use block RAM, which is a dedicated memory in most FPGAs for larger data storage. Block RAM can handle much larger memories than register banks. They are generally hundred of times bigger than the register banks. Now, when you want to use block RAM, you need to tell synthesizer that you are using block RAMs, not register banks. So your VHDL code will instruct that. FPGA vendors like Intel and Xilinx offer VHDL templates to help implementing of these block RAMs effectively. And you can implement many different and complex type of memories using these block RAMs. At the moment, we are focusing on two common type of modules, single port module and dual port memory module. We will start from the single port RAM first. So it has one write port and one read port. Address port is common for both, means read or write operation. You can write new data into the RAM block when this write enable signal is asserted, else it will read the data. Here, white text represents the ports of your RAM blocks. We define these port names in the entity declaration of our VHDL code. Red lines connects these ports to the signals which are in the black text. Now let's analyze the write cycle timing. So this is the timing diagram for a write cycle. So you will notice that we have given the write enable signal and data addresses input for one clock cycle. So it tells that you are writing data into the memory and you are also telling that at what address you are writing your data. Now here is an example of consecutive data writing. So we are writing value 8 and value 7 to address 0 and 1 respectively. So write enable signal is 1 for two clock cycles. And for the first clock cycle, the address will be 0. And for the next clock cycle, the address will be 1. So this ensures that both of the inputs are correctly stored at the right address in your memory. In this example, we are writing two datasets into the memory, but in a gap of one clock cycle. Generally, read and write operations are separated by one clock cycle for efficient data management. So at the first clock cycle, write enable pin is 1 and address is 0. So it will write value 8 at the 0th location in your memory. Then for the next clock cycle, we disable the write operation by setting it to 0. Then for the next cycle, we enabled it again for writing operation. This time we are writing value 7 at the first location of memory. So you can control read and write operation as per your project needs very easily. Now quickly understand the read cycle. So our write enable pin is set to 0, means now we are in the reading mode. You will notice that when reading from address line 0, we are getting data after one clock cycle. And because we have already talked about the propagation delays, you must visualize that why this happened. Note that these are from gate level simulation, not behavior simulation. So don't get confused on the results. Here is an example of successive data reading. In this example, we are trying to read data from 0th and first position. So we get 8 from the 0th position after one clock cycle. Next, we get 7 from the first position of memory. You can clearly see that in this timing waveform that the read data is behind one clock cycle. Means your RAM block gives the output after one clock cycle when the address is given. So in summary, we have data 8 and 7 at 0th and first position of memory element respectively. And we were reading them from memory one by one at each clock cycle. So this is our single port RAM module. Hope you are clear with the operations of a RAM module. So let's write the VHDL code for this single port RAM module. We will write our VHDL code with generics. So at the top, we declared necessary libraries and packages such as std logic 1164 and numeric underscore std. Both are from IEEE library. So it is like library IEEE use IEEE.std logic 1164.all semicolon and add numeric underscore std.all as well. Next, we have entity declaration. Here, entity is single port RAM. So let me read it first, then we will explain it. So it is entity single port RAM is generic d width colon integer semicolon e width colon integer bracket closed semicolon then port clock in std logic write data in std logic vector d width minus 1 down to 0 read data out std logic vector d width minus 1 down to 0 address in std logic vector a width minus 1 down to 0 write enable in std logic and entity. So we have declared two generics here. These are d width and a width. D width is to configure data size and a width will be used for address size. These generic parameters will give us the flexibility to use the same VHDL code for different project needs by adjusting the data sizes and address lines. If you do not use generic, then your data size and address size become fixed for some very specific requirement. So you may not able to use that stringent code for the wide applications because different projects have different memory requirements like different data size, different memory size, etc. So if you hard code them, then you need to modify your VHDL code each time when you have different requirements or different configurations. So this method is inefficient and time consuming too. So always use generics as I explained in the generic session. If this is unclear about generics, then please watch that generic video once again. Because with generics, you do not need to rewrite your VHDL code just for the configuration changes. So your design will be more flexible and adaptable. Now coming back. So next we have port declaration and we will list all the input output ports of our modules here, including their name, their data types and ranges, etc. And of course, direction. Now, important thing is we used generics like d width and a width to define our vector ranges for data bus and address lines. For example, if d width is 8, then your data line become 7 down to 0 for read and write data bus. Same a width can configure your number of address lines, and it is 2's power 4. Now this is the architecture section of our memory module. So we have two sections here. At the top, we have declaration section where we will declare or define all the internal signals which are needing for this single port RAM module. Bottom section after this begin keyword, here we will define the functionality of our module. Let me quickly read this architecture first and then we will explain it line by line. So our VHDL code is, note that green color text are comments here. So I will ignore them. Architecture behave of single port RAM is type memory T is array 0 to 2's power a width minus 1 of std logic vector d width minus 1 down to 0. Signal my RAM colon memory underscore T semicolon begin RAM process colon process clock begin if rising edge of clock, then if write enable is equals to 1, then my RAM 2 underscore integer unsigned address gets the value of write data semicolon, and if read data gets the value of my RAM 2 underscore integer unsigned address semicolon, and if and process and architecture. So first we created a custom data type and that can hold array of words. The array's length should match the number of words to be stored and its width should also match with the number of bits in the each data words. We already know how to create a custom data type in VHDL. So we used keyword type to create our custom data type named as memory T. Now the size may confuse you a little because we have used generic parameters here, instead some hard-coded inputs. So our length has the range from 0 to 2's power a width minus 1. This tells your memory locations. Means if a width is 4, then this means you will have 16 addresses ranging from 0 to 15. And if a width is 10, then you will have 1024 addresses ranging from 0 to 1023. If a width is 8, then it will have the range from 0 to 255 and so on. So this was the addresses of our memory. But we didn't specify that what type of data it will store. Like it will store character or it will store bits or bytes, what? In this code, this is also flexible. Means we are saying that it can have n number of bits and that you can configure from generics. So this is day width minus 1 down to 0 and it is std logic vector. Next, we declared a signal using this newly created custom data type. This is named as myRAM. Next is begin keyword and we will start writing our module functioning from here. Now we are using a registered process block here named as RAM process. You can choose any name because this is a register process block. So we have clock signal in the sensitivity list here. Although you should also use a reset signal, but we ignored that for the first time at the moment to make it simple. Next, let's see that what is happening at the rising edge of clock. So we have this condition. If rising edge of clock, then now we check that are we writing the data into the memory or reading the data from the memory. Means if write enable port is 1, means we are writing data into the memory. Then we have this statement. My RAM 2 underscore integer unsigned address gets the value of write data semicolon. So write data is our input data and this data will be copied in my RAM, right? But my RAM has lot of addresses. So we need to tell that at which address this data should be written, right? So it will be written at 2 integer unsigned address. Now what is this? Well, our address has the range like 0 to 255 or 0 to 1023, etc. Depends on the A width parameter, means it is integer. And our input address is std logic vector signal. So we need type conversion here, like we discussed in the previous sessions. So this statement will convert that std logic vector signal into integer number, which will be our address. I hope this is clear because this will be used couple of time in our memory section. So a quick brief, our address port is std logic vector and memory address is integer type. So in VHDL, we cannot use address port directly. We have to convert it into integer. So we perform this in two steps. First, using the unsigned typecasting operation to convert that std logic vector signal to the unsigned type, and then using two integer function to convert that unsigned type to an integer data. This integer index will be your RAM location, where you will perform your read or write operation. So that's it. This is our write operation of our memory module. Next, we have read operation, and that is simple one line code. We read data from some specific address, right? So we have address port to tell that which address to be used for the data read. And all the data are stored in my RAM array. So we will use address as an index to retrieve the data from the specific location. And then we will move that data into the read port. You can also write this read statement inside the else condition of this write enable condition. But the problem is that when write pin is enabled, at that time, what you will get at the read port means if read ports hold your last output, then it will create unnecessary latches. So this is written like that. Finally, we terminated all the if conditions and process block and architecture body. So this is our complete VHDL code for a single port RAM module. Now quickly discuss dual port RAM. So it has dual ports, like two dedicated single port RAM. Means it has two read ports, two write ports, two write enable pin, two address ports, means everything is separated except the clock signal and the memory module itself. So look at this block diagram. You will see two sections in this module. Port A is in the left hand side and port B is on the right hand side. The advantage of this dual port RAM is that two entities can access your memory at the same time. Note that memory is same. It is not like two separate memories. They are just two separate ports only. So we have one single memory and that is shared with two different set of ports and they are completely separate. Means they have their dedicated data write, data read, address and write enable port. Note that clock signal is same for the both sets. Means all the read and write timings are identical and similar to a single port RAM. So let's write the code for this dual port memory. This is the library and package declaration. So we are using library IEEE use IEEE dot std underscore logic underscore 1164 dot all use IEEE dot numeric underscore std dot all semicolon. This is entity section. Entity name is dual port RAM. So VHDL code is entity dual port RAM is generic d width integer, a width integer, then port clock in std logic, write data a colon in std logic vector, d width -1 down to 0, read data a colon out std logic vector, d width -1 down to 0, address a in std logic vector, a width -1 down to 0, write enable a colon in std logic, write data b colon in std logic vector, d width -1 down to 0, read data b out std logic vector, d width -1 down to 0, address b in std logic vector, a width -1 down to 0, write enable b in std logic, bracket closed, semicolon, and entity. This code is very similar to a single port RAM. The only difference is we have two set of ports now. Each set is labeled as A or B in the last. Means for port A, we have write data A, read data A, address A, and write enable A. And for port B, we have write data B, read data B, address B, and write enable B. Simple. So we are not explaining this much. Now this is architecture section. So this is our full architecture code for dual port RAM. Architecture behave of dual port RAM is type memory T is array 0 to 2's power a width minus 1 of std logic vector day width minus 1 down to 0. Signal my RAM colon memory underscore T semicolon begin RAM process colon process clock begin if rising edge of clock, then if write enable A is equals to 1, then my RAM to integer unsigned address A gets the value of write data A, and if read data A gets the value of my RAM to underscore integer unsigned address A semicolon. If write enable B is equals to 1, then my RAM to integer unsigned address B gets the value of write data B, and if read data B gets the value of my RAM to underscore integer unsigned address B, and if and if and process and behave. First we have data type definition and signal declaration. This is same like single port RAM, so I am not repeating that again. I will straight jump to the process section. So we have this registered process block and clock is present in the sensitivity list. Next, we have the condition of rising edge of clock. Then implemented the logic for port A of dual port RAM module. This code is same like a single port RAM again. The only difference is that now the port names are appended with the additional character A, like write enable A, address A, read data A, write data A. Next, we replicated these steps for the port B as well. This is also identical with the port A block. The only difference is now the ports are appended with the character B, like write enable B, address B, read data B, and write data B. So both of these input output cells are independent from each other while accessing the same memory. Finally, let's terminate all the if conditions, then process block, and in the last, architecture body. Okay, so that's it for today. In the next session, we will be talking about a very important concept in VHDL, which is widely used in designing. I mean, finite state machines. We will understand that what is finite state machines, how it works in VHDL, and how they are important. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.